So in this video, we're going to use the difference quotient to find the equation of a line that is tangent to a graph. And in this particular case, we're going to find the equation of a tangent line to a quadratic function. So it says find the equation of the line that is tangent to the curve f of x equals x squared minus 2 at x equals 3. So over here I drew a picture of what it is that we're being asked to find. So we have a function f of x, which is this parabola right here. And on that parabola, when x is equal to 3, there's going to be an ordered pair associated with it. So if we calculate f of 3 by plugging 3 into x squared minus 2, we're going to get 3 squared minus 2 equals 7. So we have the ordered pair 3, 7 on the graph of f of x. And we're being asked to find the equation of the tangent line, which is this line right here, the line that just touches the graph when x equals 3. So it just touches the graph at the point 3, 7. And what we want to remember is that if we're being asked to find the slope of a line, we can think of a line in slope-intercept form, y equals mx plus b. What do we need to know the equation of a line? Well, we need to know the slope of the line and the y-intercept of the line. And we're after a specific line, the line that's tangent to the graph. So maybe I'll replace the y with big T to represent tangent line. So I need to find the slope and the y-intercept. But to find the slope of a line that is tangent to a graph, we can use the tool that we developed in the previous video. We discovered in the previous video that the slope of a line that is tangent, m tangent, can be found using the difference quotient by taking the limit as h goes to 0 of the difference quotient. And we also identified that there were different synonyms for the slope of a tangent line: f prime of x, y prime, dy dx, instantaneous rate of change. Those are all synonyms for the slope of a tangent line. So the first step in finding the slope of a line that is tangent to the graph then is just to find the derivative, f prime of x. So f prime of x, the derivative or slope of the tangent lines for the graph, I can find by applying the difference quotient to the function. So we're going to take the limit as h goes to 0 of the difference quotient applied to this quadratic equation. So the difference quotient says, hey, take your function f, and everywhere you see an x, replace x with x plus h. So here's x squared minus 2. So it's going to be x squared minus 2, but everywhere I see an x, I'm going to replace it with x plus h. And then the difference quotient says subtract f of x. So f of x is going to be x squared minus 2. I'm careful to put the x squared minus 2 in parentheses so that I distribute the minus sign in. And this is all over h. So we're going to take the limit as h goes to 0. I'm going to simplify my numerator. I'm going to start by squaring this binomial x plus h. So that's going to give me x squared plus 2x h's plus an h squared when I multiply x plus h times x plus h, minus a 2 minus x squared, distributing the minus sign into the parentheses, minus minus plus 2, and this is all over h. And then if I look at the numerator, I see some things will eliminate for me because x squared minus x squared is 0, and minus 2 plus 2 is 0. So I get the limit as h goes to 0. All that's left in the numerator is a 2xh plus h squared, and this is all over h. And now when I look at the numerator, I see that h shows up in each of the two terms, which means I can factor it out using the distributive property. So to take the limit as h goes to 0 of h times 2x plus h all over h. And h divided by h equals 1 as long as h isn't 0. And h isn't going to be 0. We're taking the limit as h approaches 0. So we get as close to 0 as we want, but we never get 0. So now I'm taking the limit as h goes to 0 of 2x plus h. And now we can use a theorem from homework 3. We had a theorem that said, hey, as long as our function is defined over an open interval that contains the value at which we're taking the limit, you can just plug that number in. And 2x plus h is just a linear function, so we know the domain of a linear function is negative infinity to infinity. 0 lives in the interval from negative infinity to infinity. So by homework 3, where we did calculated limits analytically, I want to recognize I can drop the limit notation and just plug the 0 in for h, which will give me 2x. So the derivative of the function, the derivative, which is the function that describes the slopes of all possible tangent lines to the function, is just given by 2x. So to find the equation of the tangent line, I need the slope of the tangent line at this specific point, or at this specific value of x. So to find m, the slope of the tangent line I'm after, I need to plug x equal to 3 into my derivative. So I want to know, what is f prime of 3? That's just going to equal 2 times 3, which is equal to 6. So now I know the slope of this tangent line. The slope of this tangent line right here at the point 37 is 6. So I can replace the slope in the slope-intercept form of the formula with a 6. I get 6x plus b. And when you use slope-intercept form, you need to know a point on the line. So in this case, because my tangent line is tangent to f of x at the point 37, that means this tangent line contains the point 37. So when I input 3 to the tangent line, the output should be 7. So the tangent line output should be 7 when the input x is 3. And now I can solve for b, the y-intercept of the tangent line. So I get 7 equals 6 times 3 is 18 plus b. Subtracting 18 from both sides gives me negative 11 equals b. And now I can come up with the final equation for that tangent line. The tangent line formula is, or tangent line is described by 6x plus negative 11 or minus 11. There's the equation of the tangent line. So notice that was a multi-step process, but you can kind of think through it logically. Hey, I want the equation of a line. I need to find the slope of the line. The slope of the line is described by the derivative. So I take the limit as h goes to 0 of the difference quotient to get the derivative. I plug in my value of x to get the slope of the line for that specific value of x. I update the tangent line formula. I calculate the output of the function f of x at the input I'm interested in to get a point on the line, and I can use that point on the line then to find b. Process would be similar if you were using the point slope form of a line.